All right, welcome. My name is Andrew Hartnett. It's actually not Wendy Shepperd. I'm a senior director of engineering, but I do work with Wendy on a daily basis. Unfortunately, she couldn't make it, and she had asked me to help her out, and I told her of course I would do it. So my name's Andrew Hartnett. I joined New Relic about 16 months ago at the beginning of this journey that we're going to talk about to the cloud. I'm a leader in our telemetry data platform organization, responsible for our global private and public cloud infrastructure, managed services, and the data platform by which all of New Relic services are hosted, plus over 300 external integrations. So at previous companies, I'd been a New Relic customer, relying on the platform to help oversee and operate some of my most important applications and infrastructure. And with my background firmly rooted in SaaS software, hosting platforms, and cloud migrations, I was excited for the opportunity to work with one of the industry's leading telemetry platforms. So having worked on 3 different largish cloud migrations for different size organizations, I'd gained a unique perspective on what works well for different types of situations and at different stages of company growth. Over these migrations, I've learned a lot, sometimes the hard way. So today I'm going to talk to you about how we leveraged a cell-based architecture on top of AWS and AWS services to migrate our telemetry data platform from our on-prem data centers to the cloud in 1 year. So let's talk about scale a little bit. We deal with a scale that not a lot of companies in the world do. If you can imagine millions of IoT devices and servers and applications all sending us telemetry data at once, I think the actual numbers are a little bit higher than this. Right now we're at about 4 billion data points per minute. We're ingesting about 180 to 200 petabytes of data a month, and we handle, that number is not right, over 200 billion requests for that data per day. You know, tens of thousands of engineers across the world use New Relic on a daily basis to build and operate their most critical applications and infrastructure using New Relic One. Our New Relic data platform, also known as NRDB, currently ingests all of this data, and we are doubling every year. So we're dealing with a very large scale. So about our group, I mentioned we're the telemetry data platform. It is the platform by which everything resides, all of our New Relic products and services. Ingest, streaming, storage, query, it's all there. So let's talk about the architecture a little bit. So I use this slide in a lot of decks when I'm giving presentations, but this slide illustrates the heart of New Relic, in my opinion, the Kafka-based data platform. So New Relic is a full-stack observability platform that allows our customers to monitor, analyze, and optimize their entire software stack. To do this, we need to accept a lot of data, as I mentioned earlier, from a wide array of sources, everything from instrumentation libraries embedded within customer applications to mobile devices to JavaScript code running on our customers' browsers, including, and some that are not on here, data collected through OTel, data through our network partners that we are partnered with, and our new Pixie integration, which gives you everything you've ever wanted to know about Kubernetes. But almost all of these interactions, though, come down to an HTTP request. So when receiving incoming data over HTTP, our first goal is to get it out of the socket buffer and onto durable storage as quickly and reliably as possible. So Kafka is a great fit for this, since it transparently handles both disk persistence and replication across multiple machines. So once we've got that raw data written into Kafka, we then feed it through a pipeline composed of various services that aggregate and decorate and munge and do all sorts of things. And in fact, one piece of data that has come through the system could be modified up to 5 or 6 or 7 times before it actually comes to rest. So any data that flows through our Kafka cluster eventually, though, finds its way into NRDB, which is our New Relic database, part of our secret sauce. NRDB, as I mentioned, ingests over 4 billion data points per minute. And if you take that and consider the previous statement that each piece of data bounces around between topics, it starts to become clear that we need to support a very high volume of data flowing through Kafka, and all those supporting services need the ability to scale. So let me talk about NRDB real quick. So behind the scenes, NRDB is a cluster of distributed services built from the ground up for time series telemetry data. A typical large query runs on thousands of CPU cores, scanning trillions of data points to return answers to customers within milliseconds. Answering unindexed queries requires huge amounts of processing, and so we've had to optimize our telemetry data platform for speed and parallelization. Every second, the telemetry data platform serves thousands of queries for our customers who need answers stored in multiple terabytes of data. So moving all that data around to search through it doesn't make sense. So instead, we take the query to the data. So NRDB has 2 major subsystems here for historical storage and query, and then for streaming queries. So for data at rest, the system is the historical storage and ad hoc batch querying as a multi-petabyte storage system with a take the computation to the data strategy for highly parallel distributed querying. On the streaming side, you can run queries on the stream of incoming data and get results on those queries on regular intervals. So every new Relic query starts at a query router, here in the architectural diagram, that locates the data, you gotta know where it is, and sends the original query to hundreds or even thousands of workers to scan. To balance memory and I/O needs in the telemetry data platform's multi-tenant cluster, very large queries are broken up into smaller pieces. Those pieces of the queries then are sent to other routers that deliver their fastest results for recently executed queries, or the workers can scan data from disks for queries. As each worker reads its files answer the query, the process is reversed. First, the results of each file are merged on a worker, and then so forth till they come back. So we designed the telemetry data platform to scale without limits to support the unpredictable demand of our customers around the globe. And it is. We deal with this on a daily basis. Large amounts of spikes. Somebody wants to all of a sudden have all this information all at once. So the telemetry data platform ingests, as I mentioned, all of those data points per minute. And because of our multi-tenant architecture, our smallest customers actually benefit from the same massive computational needs that the big ones force us to use. So we talked a little bit about scale. Let's take it to something real here. Today is a Monday, and today's Cyber Monday, of all things. But on a normal morning, we have peak query inspected counts of 5.2 trillion events in 1 minute. On a normal Monday morning, in an hour, we've queried a total of about 441,000 years of time. So if you imagine all those time slices of data that we are returning, that averages up in an hour to about 441,000 years worth of data. And in a given hour also, we have about 16 million query processes executing per minute. So across the board, constantly computing and getting the results back that we need for our customers. So let's talk scalability. So our explosive growth led us to some serious scalability barriers. We found ourselves, before I came on board, but in 2018 and 2019, with a monolithic, single, huge cluster in production running our whole entire business, over 100 engineering teams, 800 services, 1,400 JVMs in the NRDB, all of this while ingesting 20 gigs per second. Like this massive scale threatened our ability to manage our own telemetry operations and performance. While we were operating our data centers using a container-based architecture and it was on a monolithic Kafka cluster, and we were quickly reaching the point where we couldn't physically scale anymore. Any interruption along the way, so in our Kafka cluster or in our NRDB or just in between, affected all of our customers. And it did. In 2018 and 2019, we had issues, some major outages, and I remember as a new Relic customer then that happening. So this is something that was real to us. So SaaS companies that don't constantly improve and deliver new capabilities don't stay in business for very long. So this represented an existential problem. The too risky piece here is that it was a function of the poor fault isolation that we talked about. Losing one part meant that it affected all of our business. The too slow part here is really about the complexities in owning hardware, which were being felt organization-wide, not just on our team. And then there's a connection between the two because nobody wants to be the one that deploys something that breaks production and then has to deal with all of that damage that has been caused. So obviously, it was time for us to modernize. So choosing a public cloud, we basically came down to a couple big decision points here. One was we needed to scale up quickly. We had massive growth coupled with increased demand for customers wanting their data, led to those scalability barriers that I talked about earlier. Our Kafka was already one of the largest, if not the largest Kafka clusters in the world, and we were at the physical limitations of that Kafka cluster, and so things were getting pretty hairy. When NRDB was first developed, I think it had like 10 or 15, 20 different workers that were handling all of it. Years later, when these decisions needed to be made, we were at thousands of workers. Kafka had grown to, multiple hundreds of brokers, and things were pretty tough. The other thing you get, though, by moving to the cloud for us was we also needed the ability to innovate and experiment. In our monolithic cluster environment that we had, we just did not have the ability to have something that looked like production because production was so massive. And so being able to have a place to go, a sandbox, to go test things, to build things, gave us the opportunity to break things down a little bit. And so the other thing that was coming around was the cost of our data centers. That's non-trivial, and that was something we had to deal with as well. So choosing AWS. We chose AWS as our preferred partner due to their breadth of services, global footprint, and ability to scale to our needs. Our New Relic architecture makes extensive use of Kafka, as we've talked about, microservices, everything's containerized and distributed databases. We wanted to also leverage some of AWS's managed services, such as EKS, and then MSK, which was a very big move for us. So with this move, we had the ability to change some of our architecture. So I mentioned dealing with the monolithic cluster. One problem in one area meant everybody felt it. But we wanted to take a different approach when we were going into the cloud, and that was we wanted to take sort of snapshots of our production environment and to repeat those in the cloud as many times as we could. We wanted to be able to do all the things, but we wanted to be able to make it so that our blast radius was smaller if there was a problem. Dealing with what we deal with, there's always going to be problems. but lowering the blast radius was one of our big concerns. So through our partnership with AWS, though, we kind of landed on an architectural pattern that can unlock these sort of scaling needs and these blast radius concerns called cellular architecture. So cell architecture is based on the idea that massive scale requires parallelization, which requires components to be isolated from each other. And these islands of isolation are called cells. So using fault-isolated cells enables us to run multiple NRDB clusters concurrently. The cell architecture reduces the impact of failures, as we discussed, because one cell failure does not impact other cells. And so as the number of cells grows, the blast radius gets smaller for us. As an example here, if we had just had 2 cells and one of them went down, that's 50% of our customers. But get us to 20 or 30 or 40 cells, obviously the number of customers affected by a major outage in a cell reduces drastically. So there you go, 10 cells, 10%. So we dubbed this program Project Cumulus. Clouds, Cumulus, cloud-related. I liked it. But when we launched, we had a bunch of different ideas, some of it not fully proven yet. So we started in and we chose some of the low-hanging fruit, I would say, right? So we ended up getting what we call a logging cell, which just handled some of our logging data, which at the time was a smaller amount of traffic. And so we stood it up in what we called a staging environment. We ended up launching after that both logging and metrics in cells to prove out the concept. And by the end of 2019, we had 2 platform cells running both of those products for us. And things were looking pretty good. Then came this time of year in 2019, the critical holiday period. When all of us go into production freezes because we know that our customers are going to be sending us a lot of data and their customers are going to be wanting to make sure that everything is up and they want their visibility. But we had an unexpected traffic spike through one customer, through one of our cells, and we were able to recover by moving data over to the other cell because we had room on it. And it was the first case of like, okay, we actually just saved ourselves here by having the ability to spin something up quickly, or if it's already there kind of in a warm capacity, we're able to point data to something else when we know that there's problems coming at us. So this was a major win because no customers were impacted. We were able to detect the increase in demand and in traffic, and we're able to route around it. So we then pushed forward, right? We decided to accelerate our migration. Important to note also is after that incident, evidently the lease renewal for our data center was canceled, and we were going to make this move. All right, so because of the massive amount of data that we needed to migrate and the tight integration with NRDB with all of the new Relic products, we decided upfront to optimize for speed by a combination of transforming architecture while lifting and shifting the data. So there's lots of different models when you talk about migration, but we ended up going with 2 major models. One was the lift and shift, and one was the re-architecture and move forward. So here's a timeline showing our year. The top represents our logging and others that we started off with. A reality of the observability space is that our workloads tend to be dramatically write-heavy, but when people want their data, they really, really want their data, right? It's because they're either in the middle of an issue, they need to know what they need to do in order to go fix it, and this observability becomes very important. So while most of the data we collect isn't looked at, our customers, as I said, when they do need to, they really need to look at it. And so we needed to preserve the ability for us to service writes in a timely manner as our most important goal. So let's talk about the migration itself. To start with, this is a good snapshot of our data center and what it sort of looked like. This is from our first cells, which handled logging and metrics data for us. So in our data center, shows everything flowing through Kafka and then eventually landing on InterDB. The presentation layer here refers to APIs and UIs that we make available, but they're not technically part of the cell-based architecture itself. So one of the first things that we did was we introduced a smart routing layer. It was a combination of using Cloudflare and Fastly between our DC and our customers. And we needed to do that because as we were migrating, we still needed to make all of our data available to all of our customers. So we needed to know if a customer's data was here, here, or here. And the smart routing layer was the key to that. So next, we created scaled-down versions of our DC architecture in AWS. And so this is the cellular-based architecture. Basically took a snapshot of our architecture, and we've just replicated it in AWS. These mini DCs, or cells, are all isolated environments, even down to being isolated in different AWS accounts. As this was being designed, looking at managing a single giant Kafka clustered into n number of mini clusters, we also felt it was important to keep the overhead of running those clusters lower. So we chose to partner with AWS to use their managed Kafka service, MSK, and that was a great choice for us. So while going through the migration, we architected and built a new service called the query router that we talked about. The query router actually generates and maintains a per cell Bloom filter published to a central source of truth so we know where customers' data is. So as we were migrating, we obviously still had Kafka set up in our data center. So that query router needed to go back and forth between the two. What we ended up doing was treating our older environment, our data center environment, as a cell itself. So if you looked through some views, it just looked like we had a very, very large cell, but as part for the routing, it made sense for us to be able to do that. So some of our workloads involve aggregating data that might reside in different cells. Customers that use lots of different products might have their data spread out all over. We just needed to know where it was. We also utilized Kafka mirror makers to mirror a small subset of the data back and forth, so we had access to the data when we really needed it. So I like this slide. So we needed to migrate data incrementally as we were not going to be moving everything at once. We needed to design our migration to handle gradual data transfers into these isolated environments. So for each data type, event type, metrics, logs, traces, all of that, what we did was in our production monitoring environment, we have our own environment that monitors ourselves. And by the way, all of my teams are, fanatic New Relic users for all of our services. We drink our own champagne, as we say. But in each one, in our production environment, we deployed its pipeline to the cloud. Then we moved a few of our accounts to the cloud first, sort of like just sticking your toe in the bathwater before you go plunge in, just to make sure things were good. But once we did, we were able to then go replicate this in production a little bit faster and then gradually scale up to all accounts into the cloud. And again, by adding that routing layer first, we did learn some important lessons before moving all into AWS, and we were able to migrate and shift data ingest to cells and leverage MSK. So now we needed to go back and say, okay, all those things that we've learned, all those pins that we stuck in the wall because we knew we had to come back and do some things, it was time to modernize our orchestration layer. So not moving to MSK and then EKS would have really pushed out our timeline significantly, but being able to consume these managed services helped us out a lot. Again, migrations are tough, and there's lots of different ways to do it. We've talked about two of the big managed services that we ended up moving to, MSK and EKS. For our migration to EKS, we chose to what we call lift and shift and then optimized. The reason we did that was because a lot of our services, while they were container-based, were not ready to take advantage of everything that EKS brought to the table. To really take full advantage of it, we needed to do some work first. And so we shifted to our own Kubernetes environment first, made a bunch of changes to services that we knew needed to have the changes made before we can jump in. So we then adopted EKS by one at a time building new cells with EKS and starting to shift traffic to them, and then decomming the old cells. So before the migration started, again, that smart routing layer was created. And during the migration, we moved data directly into MSK and our services into our own Kubernetes environment. We then took time to upgrade and update the systems that we knew needed to be upgraded and updated. And then we started to move services into EKS, as I said, to take advantage of all the reasons why people use EKS: auto-scaling, spot instance support, and then being able to have a single control plane that manage all of your Kubernetes for you. So this is actually my favorite chart. We call it the Shepperd chart. And what this shows is a timeline from near the beginning when we started our first cell to 10 or 11 months later when we had finished the data plane migration. What you see here is the number of cells being spun up are represented in all those colors, and the blue along the bottom represents our old data center, and then eventually that goes to 0, which was pretty cool. What this doesn't show is that later, probably on this depiction, further out to the right, we have probably doubled the number of cells since this was originally fully migrated, just through normal growth. And so a little celebration, we ended up moving 100% of our data ingestion in just under a year, which was awesome. Let's talk about challenges, because I thought of maybe trying to rename the slide the good, the bad, and the ugly. But some of our concerns: capacity management, cell comms and decoms, I mentioned that just a minute ago. And then obviously all of us have to deal with cost, because none of this is actually free, and it gets more expensive than you realize very quickly. All right, and also a couple key surprises along the way, right? COVID-19 hit. Our business went through a large transformation and shifted to a new consumption-based billing model. We launched the telemetry data platform as a product itself, all while doubling our ingest. And then, over the last 6 months or so, we're all been dealing with the Great Resignation, right? Keeping talented people in place to build and define our new systems has become a little more difficult. But we did have some wins. Right away, I mentioned the first real big incident where we were able to route traffic to a different cell. We now have, I think many more cells than we had in there in the graph that we showed earlier on the Shepperd chart, but it has given us improved performance, capacity management. We now have a very flexible and very scalable architecture. EKS continues to do all the things that it does, and it helps us with a lot of our services for scaling. And then at the end, we also decommed our first DC. It's one thing to build something, but I almost find it just as satisfying to be able to decom something and let it go. So around the improved performance, we're now operating dozens and dozens of cells. EKS is the control plane across all of them, which has enabled us to be able to start getting heavily into auto-scaling based off of whatever triggers that we can define. Our performance, our platform performance and capacity management by using this sort of automation around auto-scaling and other automation has been very powerful for us. So for example, we have introduced some different scale sizing. We do have some customers that require us to scale some of our, like with the beast resources, because they handle the largest workloads. We have cells that are specifically tailored for customers in highly relegated industries, think FedRAMP and HIPAA. We have the ability to pin customers to specific cells in case we need to know exactly where all a customer's data is and we need to shift traffic quickly. The cellular architecture provides all that flexibility to meet the needs of our customer, because that's what it's all about. So some numbers. We're actually, right before I came here, we are actually at around 25,000 total nodes, and we're actually over 250,000 pods, right? So we deal with a massive scale. We are one of EKS's largest customers. But customers trust New Relic with their most sensitive and timely data. We rely on services like EKS. Because we do, New Relic can focus on its core competencies instead of data center and hardware management. Getting out of the business of managing infrastructure is one of our key objectives and will enable us to be able to do the things that we need to do for our customers instead of managing hardware. AWS does that very well. So now all of our telemetry ingest is processed on AWS infrastructure, and the new architecture has already paid off in major improvements in platform resiliency, performance, and scale. Did I mention that we decommed our first data center? All right, so here's some of the lessons learned. I joined New Relic 16 months ago, and so this had just started when I came on board. So I have been here for all of the lessons learned portion here. The first thing is that observability is key. It just so happens we're an observability customer or company, and so that makes it easier for us. But it's really important to instrument every part of your system, both your system you're migrating from, the way that you're doing the actual migration, and then the end system as well. The tight integration between AWS and New Relic made this sort of observability simple. By having a clear picture of what was going on, what changes failed, and when they failed, we could move at an even faster pace. So our observability enabled us to detect failures and remediate in minutes versus not having an understanding of what was going on. It's very powerful. So as I said, all of our systems are fully instrumented. It hugely accelerated our ability to make large-scale changes and migrations. We knew exactly where and when bottlenecks appeared. And rather looking at low-level host metrics, our teams had visibility into the topology of our systems and can look closely at anomalies that were detected instead of relying on something so low-level. Our engineers use our new Relic platform to simultaneously visualize large-scale data migrations from our monolithic private cloud data center to a microservice cell-based architecture, and fully instrument Kubernetes workloads to detect individual system performance changes across the migration. So this level of observability and information gave us the confidence to move massive amounts of data, as I said, in a very short time, and quickly switch production traffic to our AWS EKS environment. In addition, early on in our migration journey, our engineering teams used our own platform to understand our current private cloud compute needs. And so this made refactoring to EKS an even more obvious decision, as we were able to take advantage of cost savings that we were able to detect. So when systems are going through massive change, it's easy to get overwhelmed. I talked about being like down in the weeds, but trying to monitor every metric, event, and static alert, there's just so many unknowns. And so to manage and mitigate the risk of such large system change events, applications owners and architects need to have the ability to see their system in high cardinality and high dimensionality. And so having a tool like this sort of heat map that gives you the idea that there may have been an anomaly detected and the ability to drill in quickly really helped us along the way. And so, just even to simple burn down charts. You can see across the top here data that's being moved from one place to another, and then on the bottom left, something as simple as like, hey, here's the amount of data in our cells. And so being able to understand like what is our maximum capacity and when do we need to add another cell to our environment. Having the ability to track all this just becomes very key. Next lesson learned, don't plan for the happy path. Stuff happens. We deal in a world where we rely on others, we rely on fiber, all of that. Things can change. Customers can do things to you. Even the best laid plans will have surprises and discoveries. Plan for these surprises and discoveries along the way. One key was to start small and then iterate. I talked about sticking your toe into the bathwater first. Try with your own data, right? Because we are actually one of our own largest customers. Sending our own data first made sense. So our iterative approach through each data type enabled us to make changes and evolve our automation throughout the migration. Key, continuously build new cells. We have a goal of having an average cell life of 90 days, right? By trying to enforce that and push that, you get the ability to make your changes with new cells instead of having to do it with cells that are actually dealing with customer load. AWS provides all the APIs and managed services we need to continuously build and decom cells, so we do it. As a result, our platform reliability has improved significantly, and we have reclaimed engineering capacity that was previously spent on infrastructure. Another lesson learned, invest in planning and communication. Cloud migrations in general are a company-wide event, and they should be treated as such with company-wide communications. They're also a culture changer. They are a catalyst for culture change. If you are leaving, for example, like us, when we were leaving this monolithic data center culture that we had, we built everything ourselves and we were very proud of it, to then having to let somebody like AWS manage our infrastructure, it was a change. And so over-communicating becomes very important. And also, don't keep your customers in the dark. It's also important to let them know, here's the reasons why we're doing all of this. We may experience some bumps, but this is going to get better. So what's next? We are going to be moving additional services to the cloud. We have new cell types. The cells that I've been referring to were our data plane. We also have our control plane that we are going to be actively moving. Those are differently shaped and obviously different computational and infrastructure needs, but we're working on that. Also, geographic expansion. What we want to do is we want to get closer to our customers, right? By expanding our global footprint in new cells in additional regions, AU, for example, Japan, give us more opportunities to leverage edge data services and give our customers that flexibility. And then cloud cost optimizations. There is a whole track here on Finops. One of my good buddies, Mike, he runs our Finops organization that we established, a dedicated team to focus specifically on cost optimizations. Who's spending the most? Do they need to be spending the most? And partnering with those teams to help them look at different ways of either handling load or auto scaling or whatever it should be. But being able to provide cost insights to our consuming teams has become very important and is now part of each one of our projects. And when we look at adding new something, there's always a cost item in there to talk about. So all of this was made possible through our partnership with AWS, and we could not have done it without them. I look forward to the future and a continued successful partnership between AWS and New Relic. Thank you for listening.